awful quadratic, somewhere here at 3, that is 9 high, and if I was to draw a tangent at this point, that tangent would go 1 across and 6 up. The slope is 6. So you guys can very quickly tell quite a lot about this graph. You can tell not only a location, that's your old function notation stuff, but also a slope. What about if I gave you x is -2? -2, how high is it? 4, because -2 squared is 4. Yeah? And what's the slope of the line here? -4, because we're putting into this one. And that gives us -4. So, we'll do a few more of these ones, because they're long algebraic problems. But if you start with a function, and do first principles on it, you end up with f dash x, which is another function. This one doesn't tell you its location, it tells you the slope of the line at that location. So the original function tells you how far up you go, so 3 across 9 up. This one tells you how steep the line is at that point. And the reason we're particularly interested in slope is because it can tell us where the steepest points are, it can tell us where the flat points are. And if you think about a graph that does this, at this point here, the graph is flat, so the slope is 0. Where it's flat will always be a maximum point. Most of the time be a maximum point. So you can find optimal solutions. And this is where we're going over the next couple of weeks, is we are going to look at how to use the slope to tell us different things. Maximum, minimum solutions, etc. But that's sort of forecasting where to go. First, we need to get comfortable with this idea of first principles. And I think I have another couple of examples for you. Alright, let's do this one. I will clear myself some space. You guys might potentially be quite confused. Take some notes. And
3 minutes.
We've got 3 minutes. I will work it quickly. You guys alright? What are we not telling anyone on camera, Z?
On camera?
Don't
Don't worry about it. Especially not here.
Okay. Alright, our function is y equals 2x squared. And we want to find f of x. Oh, fun little side story. You see how f dash x, they say, is dy dx? And you know how we've been almost interchangeably been using f of x and y? Did I tell you the story behind y? There were 2 rival mathematicians.
You told us.
I told you this, yeah. They both basically invented it at the same time, and ever since then we've been having to roll with the same pair of notation simultaneously. That's it here. This is the slope when x, this function's equal to x, and this is the change in y over the change in x, meaning rise over run at that particular point. They mean the same thing, they're just written differently. This is much easier to use, the f dash one, but you'll see both. Alright, here, f dash x, and remember that's the same as dy dx, or the derivative, is equal to the limit as h approaches 0 of f of x plus h, take f of x over h. This is always coming from the substitution of x plus h into the function. So it will be 2 lots of x plus h squared, then take away f of x, so take away 2x squared over h. And now the general plan from here is we expand, simplify, collect everything together, and we should factor out an h. Once we've factored out an h, then we can evaluate the limit, and that will give us our function, or our derivative. I'm going to run out of time, aren't I? Alright, we will pick this up tomorrow. Thank you all.
Yeah, tomorrow.